So we will start with the first contributed talk of today, which is about adaptive regularizing Tucker decomposition for knowledge graph completion by Shimin from the Hong Kong University of Science and Technology.
Hello everyone, my name is Shimin. Today we are going to give a presentation about our work, adaptive regularizing Tucker decomposition for knowledge graph completion. This is joint work with Yao Shimin and Zhang Yongqi for Paradigm and HKUST. First, background. So what is knowledge graph? Knowledge graph plays an important role in exploring and organizing knowledge bases, which is applicable to many real-world applications. Generally, real facts in knowledge graph are represented in the triplet form: head entity, relation, tail entity. Given a triplet, the crucial task in knowledge graphs is to verify whether the triplet is a real fact or not, which is named as knowledge graph completion. Recently, embedding approaches have been developed as a promising method to tackle this task. Knowledge graph embedding approaches encode the knowledge graph into low-dimensional vector spaces, such as entity embeddings and relation embeddings, E and I. Then the scaling function, FHRT, is utilized to measure whether a triplet is real or not. Here is a scaling function example from transit technique. Related work. Among kinds of scaling functions, tensor decomposition models have been demonstrated their superiority due to impressive guarantee and better empirical performance. Generally, there are two decomposition models. First, CP. The scaling function is generally based on the inner product of the embedding vectors. Another is Tucker decomposition. The Tucker utilizes a three-order tensor X to represent a knowledge graph. Xijk equals to 1 represents that the fact ER_ijk is known to exist. Otherwise, the element Xijk is set to 0. Then, Tucker factorizes X by Tucker decomposition by such form. So here, this is a representation of knowledge graph. This is a Tucker cotensor, and this is entity embeddings and relation embeddings. Generally, the Tucker cotensor encodes the interactions between the embeddings from the dimension level. After the background and related work, now we are talking about our motivations and how to formulate our problem. However, the Tucker tensor requires the cubic complexity, which is hard to train and easy to overfit without sufficient data. But CP-based tensor decomposition models, such as DSMAS, complex, simple IE, achieve good performance without introducing the dense cotensor. So we have one question. Is it essential to learn a cotensor with so many trainable parameters to model the interaction between the entity embeddings and the relation embeddings? We observe that CP-based tensor decomposition models can be regarded as have a special cotensor with sparse constraint. So here is several examples. First, this is the cotensor in Tucker. The gray area means that it is all elements needed to train. As for the rest of examples, so the white area means that there is an element set to 0. For example, in the DSMAS, there is only in the superdiagonals the element is non-zero. So we are motivated by these observations, so we think about whether we can utilize such sparse constraint to regularize the Tucker cotensor but still achieve the good performance. To elevate the overparameterization issue, we propose to regularize the Tucker decompositions. First, we do the embedding segmentations. we divide an embedding into multiple segmentations as h equal to h1 to hm, and same for the relation embedding and the tail entity. Then we define the diagonal tensors. We define three diagonal tensors, I1, I0, I-1. For example, in this area, if we select the I1, we think that I2 has the positive correlation with H1 and T1. If we select the I-1 for this area, we think I1 have negative correlation with H1 and T1. Here we formally give the definition, except for embedding segmentations, we also need to divide the cotensor into m^3 segments. Note that each GRJK can be independently chosen from O, operation set O. Then the scaling function is defined as a summation of different segment area. Now we regularize the cotensor with sparse constraint, right? Furthermore, inspired by the automated machine learning technique, AutoML, we proposed to adaptively regularize the task decomposition for any given cage data. That is because we think different cages have various properties, thus we need to search suitable regularized cotensor to capture it. Thus, we form our problem into a search problem. We can see that the search problem has two levels. The low level is to optimize the cage embeddings, while the up level is to search suitable cotensor. Then we'll talk about how to solve this search problem. So optimize the search problem is a non-trivial task due to the large amount of candidates. For example, when we set M to 4, there are totally 3 power 44. When we set M to 4, there are total 3 power 64 candidates. It is hard to search a suitable one from so many candidates. Thus, to enable an efficient search method, we first design a continuous way as this is form. So generally, it's an illustration. So we utilize ARJKP denotes the weight between the operation with the cube. So we can take a look at this illustration. So this is our scaling functions. We need to select a suitable weight, a suitable diagonal tensors, and then we can utilize the weight to denote the connections or the correlations between the operation with cube. And then we can train the weight and select the better one. Thus, to solve this problem, here is how we solve this problem. First, we initialize the architecture weight A0 and embeddings X0. While not converged, we do an alternative way. First, we optimize the embeddings, and then we optimize the architecture weight. In the embedding optimizations, we first sample a mini batch data from the train data, and then we sample a regularized cotensor based on current architecture weight, and then we update the embeddings. So after that, we fix the embeddings, and to optimize the architecture weight, we sample a mini batch data from the validation set and update the weight with the help of one AutoML technique. Finally, we can get the final cotensor from the weight, architecture weight, and achieve embeddings by training the cotensor from scratch to convergence. Finally, let us take a look at our experiment result. We follow the previous work to choose the link prediction as to compare our effectiveness. And we conduct our experiment on the full benchmark dataset We can see that the proposed method art continuously achieves the better performance in all the datasets. This is because we choose the adaptively, we choose an adaptive way to search suitable cotensor for each dataset. And as for Tucker, we can see that we almost achieve better performance than Tucker in all comparisons. And because we regularize the cotensor to solve the overparameter issue. And this is effectiveness comparison. How about the efficiency? So the time cost of art is cheaper than Tucker. Why it is longer than the simplest tensor decomposition model this must. Actually, because we regularize the cotensor and we conduct the more cheaper computation than the Tucker. And how about case studies? So in generally, we show that art indeed search the different cotensors for different cages. This is reference. That's all. Thank you.
Thank you, Shimin, for the presentation. So we have a couple of questions in the chat. I think the first one are from Cesar and me, and actually are quite related. So maybe you can, do you see the question in the chat? And can you maybe read them and give short answers to them?
Okay. So for the first question is how do you choose how to segment the embeddings and how does this affect the performance? So in generally, we set a hyperparameters M to segment the one embeddings into multiple segments. So it should be tested or based on the empirical performance. So generally, we will set the number of segmentations to 4, and does this affect the performance? So in our test, so in effectiveness, I think we think it does not change at all. It does not affect the empirical performance when we test. But as for the efficiency, yes, it does a little affect the performance. And in addition to the number of yes. So in general, we didn't include this, but in previously published paper in SD, we studied the permission of the component of embeddings affects the performance because um, a, a lot of permutations can be regarded as equals to each other. So we have a peer study on SD published in AutoSF. And a next question. So how do you define segmentation of the tactical? Next question, how do you define the segmentations of the tactical tensor? Such a full space is too expensive. Sorry, could you please stop sharing so I can share my slide?
Shimin, can you stop sharing? I think you can now share your slide, Shimin.
Okay, yeah, thank you. Yes, so here. So in generally, we search our search yes, it is too expensive. So we utilize the weight to model the interactions between the three candies with one cube. And generally, in each step, we will actually sample the like potential and based on the weight. So the weight is actually the probability, the sample probability, and then we can optimize the probability, optimize the weight. So if some combinations of some component indeed make a progress or improvement in this sampling, so we will increase their rate. But if they perform badly, so we will reduce their weight by gradient descent. So this is how we optimize them. And for the next question, how can it be called by you? Can you discuss particular structure versus particular? So yes. So here we think our method is not it's not a relational wheel. It's more like a data wheel. So in generally, we cannot to find a special structures for one specific relations. But if you extend this work to relation wheel, such as for each relation patterns, you could search a one sparse potential. We think yes, we could. This method could discover. But in this paper, we do not. We only extend this work to data wheel. It's not a relation wheel. Okay, the next question is related to optimization. So sorry, maybe uh, what is the range of the variables when searching the architectures? How to get to the range by gradient descent? Okay, so in generally we in this part we optimize the embeddings is much easier in HBook embedding. I think the most question is related here. So how to optimize the weight and when setting within a sub and super range. Uh, Generally, we update this weight based on one last paper. As you know, we think it introduced the personal personal step, so it could be safe and it could be safe to optimize the architecture rate. And for the next question, how much will the calculation cost per search increase if the number of percentage is increased? Oh, yes, that's a very good question. So the calculation cost is actually the only based is indeed so depend on the app. Generally, we think the calculation increased is can be regarded as the cubic complexity regarded as the number of segmentations. So the number of blocks could not be set too large. Um, in the real test, we think that each segmentation is actually can be uh, it, in, actually can be regarded as the different segment meanings in the relations. So indeed, the segmentation, the number of segmentations, so it does not need too large. Yes, but it's probably it does exist if the number of the blocks increased.
Yeah. Thank you, Shimin, for the answers and for the great talk.